All right. We are on just finishing. Just a second, I got to get our book up. Yeah, Grant said he's not going to be here today, so.
Okay.
He wants to retake the test tomorrow. Do either of you want to retake the test, or are you okay with your score? Test 2. You don't care. Not sure.
I'll email you about that, Kevin.
Okay, all right.
Thank you.
Yeah, because if you do it tomorrow, would be a good day to do it since Grant's going to do it tomorrow.
Sounds good. Is it going to be during class or after class? Or what?
It'll have to be after class. That's why it's a good day to do it. So that, and then just sit at that back table there, because I don't think she has a lot of people in this class.
Sounds good.
All right. When we left off, we were on. Oops. We left off right with this equation. Suppose a second cube C2 has twice the volume. Oops, you can't see that. Has twice the volume. What is true about the surface area? And I gave you this relationship, and that's where we left off. If the volume doubles, the surface area only increases by 1.59, because you can find what that is by taking 2 to the 2/3, and then you will get the correct answer. We're starting 15B, and I have here a recipe for a super moist Betty Crocker cake. Now, I have a question for you. You might not know this, but the baking times are different depending on what kind of pan you put it in. Okay? So the choices are 13 by 9, 2 8-inch, 2 9-inch, 24 cupcakes, or a 12-inch bundt cake, or 12-cup bundt cake. Now, does anybody know what a bundt cake is? Because that's usually where we fall apart. It's kind of like an angel food cake. It has a hole in the middle, and then it... So, which of those do you think you should set the timer for the shortest amount of time? Do you want the choices again? 13 by 9-inch pan, 2 9-inch, 2 8-inch, cupcakes, or a bundt pan.
It would be like the biggest one because it's flat.
That's not a bad guess. You're on the right track.
It's going to be the one that's like thickest because it would take the longest to go to the center.
Okay, but I said which one you set the timer for the shortest?
The shortest, though.
Shortest time. So now I think you'll get it. What?
Cupcakes.
Okay, so he says cupcakes. Here's the way I explain it. The cupcakes, the center of the cupcake is close to the outside. Okay? Compared to all the rest of them. Okay? So if that is true, then just compare the 2 9-inch and 2 8-inch round pans. Okay? Which one of those do you think will cook fastest? Bake fastest. 2 8s? Why is that?
Because you said before cupcakes, if it's closer to the edge.
I can see why she would say it. So what she's saying is, since it's smaller around, it's going to cook faster. But what happens to the cake mix as you squeeze the cake mix into a smaller circle? It's going to get thicker, right? So here's what they say. 2 8-inch take 30 to 35 minutes. 2 9-inch take 25 to 30 minutes. This all has to do with an idea called scaling And the example that they give for scaling is on page 267. Now, when I first looked at this page, I was like, oh, that's kind of a weird way to draw an elephant. But if you notice, they're drawing not just an elephant, but a horse, a cat, a dog, a gorilla, a mouse, and I guess that bottom thing is just a mouse. Isn't that kind of cool? A little bit? Whatever, Kevin. Keep your thoughts to yourself. Here we go. Think about the amount of food that different animals need to survive and thrive. How would you compare the amount a mouse needs to what an elephant needs? Well, obviously, an elephant is going to need more food, right? But how would you go about making a comparison? How much you eat compared to how much you weigh. That would be a good comparison. If one species is twice as large as another, do you think it requires twice as much food? Well, that's what we're going to explore in today's lesson. Our formula is Kleiber's Law. Kleiber's Law says R as a function of the mass, in other words, the metabolism as a function of mass is 70 times the mass to the 3/4. Okay, so on the next page, we're going to fill in this chart for the mass they give of a dog, the mass they give of a horse, and the mass they give of an elephant. So we're going to just take those three and multiply them out. Dog, horse, elephant, mass, and then R is metabolic rate. And then later on we're going to do heart rate, so I'm going to put that letter into my chart also, even though they don't have that column yet. Okay, so the mass of a dog is 16, the mass of a horse is 256, and the mass of an elephant is 4096. What'd you get for the metabolic rates? Let's do them. Are those answers approximately what you got? Okay, question B says, we're on 2B. 2B. So, horse divided by dog, we want just the mass. Horse divided by dog. What do you get? $16. And then the other part, metabolic rate. Is it 8? Okay. Part C says elephant divided by dog. Elephant divided by dog. What'd you get? 256. Do I have this first one right? Is it 16 and 8? Okay, 256. And then what's this one over here? 64. So if part D says, now we want the mass to double. What does this over here become? Well, if you notice, if you take 256 divided by 64, you get 4. If you take 16 divided by 8, you get 2, right? So 8 is 2 to the third. 64 is 2 to the third. So for this answer, we would have to know that this number is 1.68. .68 is the square root of 2 to the third. In other words, for each one of these, if you take this number to the 3/4, let's try it and see what we get. $16 3/4 is 8. 256 to the 3/4 is 64. 2 to the 3/4 is 1.68. So if the mass doubles, the metabolism increases by 1.68. Think about it this way. An elephant weighs as much as 256 dogs. Compared to the amount of food that 256 dogs eat, it would only eat 64 times as much as one dog. 256 dogs would eat 256. So it's cheaper to own an elephant than to own an equal mass of dogs. Now, anybody own 256 dogs? I'm not saying feeding an elephant is going to be cheap. What I'm saying is feeding an elephant is going to be cheaper than feeding 256 dogs. Let's think about it in terms of people. If you have a person that weighs twice as much as another person, their caloric intake would only be 1.68 times as much. Okay? So while you have to eat more food if you weigh more, you don't have to eat twice as much food. If you do eat twice as much food, do you see a problem arising? You're no longer going to be twice as big as the other person. You're going to be 3 times, then 4 times, then 5 times, then 6 times, okay? So about the age that you are now, I'm just giving you advice from an old person. About the age that you are now, don't keep on eating more and more every year. Okay? Keep it even, Stephen, is the way to go. If you don't, you will. And notice I said that the day after Thanksgiving break, right? Did anybody eat too much on Thanksgiving Day? A couple people. Thought you had to work.
Oh, I was sleepy.
Oh, okay.
I was eating so much. I had 2 Thanksgivings to go to.
There you go. Okay, so part D then, if an animal's mass doubles, its caloric intake will only increase by 1.68. Suppose the mass of one animal is K times the mass of another animal. How do their metabolic rates compare? K to the 3/4. So you just take that number and raise it to the 3/4. I like this because it shows that that number is useful. Really what's happening, if you wanted to look at it, is that you're taking the cube root of K to the 4th. In other words, you, I'm not going to say quadruple, you to the 4th power, whatever mass the thing is, and take the cube root of it, and that's how much food it takes. Next one. Let's figure it out for a person. So let's go back to the chart here and put in your mass. Well, my mass, I have to take my weight, 190 divided by 2.2, because it's 2.2 pounds per kilogram. So I weigh 86 kilograms. So 86, and I have to take that times, here's my money, to the, so second function answer, to the 3/4, and then multiply that times 70, and it's saying I should get about 1,983 calories. Do it for you and see how many calories you should burn. So take your weight, divide by 2.2, and then to the 3/4 times 70. Does it kind of look like a good number for your weight? Is there anybody that's less than 900? Shouldn't be. How many calories are girls supposed to consume? Like 1,200? Does that sound right? Anybody know? No. I eat a lot more than that. Yeah, but you're kind of active. You have to show up at that store and sell half a pair of shoes. So.
You get so counted.
Okay.
Divided by 2.2.
Divided by 2.2. Take that number to the 3/4, and then multiply that by 70. Is there anybody that's over 3,000 calories? Now, I believe pregnant women are supposed to have about 3,000 calories. Why is that? Because they're eating, what's that? They're eating for 2. Okay?
They're not.
I'm actually eating for 2 also. It's just, there's only one of me. Doctor, that might be the problem. I'm eating for 2 and I shouldn't be, huh? Who just said that's not true?
It's not. A normal woman can eat her normal amount of food and still be all right and have the baby get as much nutrition as it needs as long as she's taking all of her vitamins as per needed.
Show me a medical study on that, because I'd be interested to see a medical study that says that. I've never heard of that before.
That's what it is. I haven't done a ton of research into it myself, but that's what
Cool. Show me the research. I'd love to read it. I'm always interested in new things. How about if you're breastfeeding? I would think you'd have to eat more then also. Okay, here we go. Next one. So now we've taken care of mass. Let's look at the next one. Heart rate as a function of mass is 241 times mass to the negative 0.25. First off, what are some of the ways to write m to the negative 0.25? Let's hear some. Well, what's the negative tell us? 1 over m to the 0.25. 1 over the fourth root of m. Do you see why it's the fourth root of m? Because remember, the index is the denominator. 4. The power here, 1, is the numerator. 1/4 is 0.25. Okay, so then it says, use Kleiber's law Let's go back here and fill in these animal heart rates for Kleiber's law. I don't think I've got that in a table form. What did you get for heart rates? Let's give me some numbers. Dog. Nobody got it? Do you know what to do? 16 to the negative 0.25 times 241 is 120. Did anybody get 120.5? Yes. Oh, okay. So what did you get for horse? $60.25. And elephant? Did you get 30.125? So if the mass doubles, actually that's not doubles, if the mass doubles, the heart rate only increases 2 to the negative 0.25, only increases by 0.84. Okay, so when they take an ultrasound of a pregnant lady, they'll listen to the heart rate, and the heart rate goes boom, 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 boom. Why? Because the baby doesn't weigh very much. In fact, they do use the heart rate to determine how much the baby weighs. They just backtrack. What's that?
I said mine was pretty slow then.
Why, you were a small baby?
I was a fat baby.
Oh, you were a fat? So yours would have been, yeah, you're right, pretty slow. Man alive. Were you ever, no, I'm just kidding. Things you don't comment on are when ladies say, does this dress make me look fat? That is a no-win situation. Page 219. So, let's go through the process of starting with M. What's the first thing we do to end up with 241m to the negative 0.25? To the negative 0.25, right? And we get m to the negative 0.25. Then what do? Take that times 241, and we get 241 m to the negative 0.25. Remember, you always do logarithms and exponents first, then multiplications and divisions. Notice we don't have any additions and subtractions, so we don't need to do that step. How do we undo it? Well, we start with the heart rate. What's the first thing we're going to undo? And we get h over 241. Now be careful about what's the undo of to the negative 0.25. Remember, that's this right here. So it's going to be to the negative is still true because we're still going to be in the denominator. Right? To the what power? Negative fourth. So we will end up with 241 to the fourth over h to the fourth. And that will, 241 to the fourth over h to the fourth. And that will be our, I gotta make sure that's right. I think you undo a negative by keeping it negative. Two 41 to the fourth over h to the fourth. Yeah, that's right. Last thing. Use this information from Part C to write Kleiber's law. Oh, let's go back here and figure out what our ideal heart rate should be. So if I weigh 86, I take 86 to the negative 0.25 times 241, and my heart rate should be 79. My heart rate is actually about 60. So I'm my heart is going too slow. No, it's 60. I weigh more than I should. Well, that kind of stands to reason. Should have figured that one out, but I didn't. Anybody have a number bigger than 100? You'd have to be pretty skinny to be bigger than 100. Anybody have less than 40? You'd have to weigh almost as much as an elephant to have a heart rate of 40, right? Because theirs is 30. Okay. No, the last thing it says is use the information to write rewrite Kleiber's law so that the metabolic rate is a function of heart rate. R is a function of M, which is a function of H. Now remember, they gave us H is a function of M. We just calculated M is a function of H. So the way you do that is you write Kleiber's law. Kleiber's law said 70, right, times something to the what power? Three-fourths, right? Kleiber's law. Something to the 3/4. What is that something? And in this case, this is M. 241 to the 4th over H to the 4th. When you multiply numbers, you add exponents. So we're going to multiply 241 to the 4th times 3/4. I'm sorry, when you raise numbers to powers, you're going to multiply exponents. So 241 to the 4th to the 3/4 is 241 to the 3rd, because the 4th here cancels the 3 there, over H to the 4th to the 3/4 is H to the 3rd. So remember, the way to get a function of a function is to get the variables so that the variable from the first one, remember we're going to put in the input, get an output over here, and we're going to take that output and make it the input of our other machine, right? So you get it so that the output from the first function is the input to the second function. Page. Two 21. A while ago, we asked this question: is the square root of a number always bigger than the fourth root of a number? Do you remember we had that question a few weeks ago? And somebody in Chippewas gave us the right answer, but I don't remember who it was. I mean, Menominee, excuse me. Somebody in Menominee gave us the right answer. Was it Grant? You don't remember giving us the right answer? Well, that's what we're going to study today. Is we are going to graph different powers and see which is bigger. Use your graphing calculator or graphing app for the following functions on the same set of axes. So let's go to Desmos. Okay, so it says graph. Okay, here we go. So I'm going to graph x to the 1/2 x to the 1/4, x to the 1/6. And if you notice, x to the 1/2 is above x to the 1/4 is above x to the 1/6. Sketch the graph. It says, what patterns do you see for the domains of these functions? What's true about the domain? Very good. So the domain of a fraction that is even is bracket 0, comma, infinity, close parentheses. So I wrote 1 over e for even number. The domain goes from 0 to infinity. Remember, you can't take the square root of a negative number, right? Remember that? Okay, so this is just an expansion of that, and it says that. Okay. Well, when we sketch those, I want you to focus in so that this is the point 0, 0, and draw it so that you can see the point 1, 1. So on your graph, let's focus in on those 2 points, 0, 0, and 1, 1. So I'm going to change my axes to go from 0 or negative 0.1 up to 4. And I'm going to go on the y-axis from negative 0.1 up to 4. So I'm going 4 in each direction. My top graph is x to the 1/4. So I'm going to draw that in, one square root of x. So that's x to the 1/2. I'm going to draw the middle one in blue. Did I lose my blue marker? I'll make it purple because I don't see my blue marker here. So at the beginning, it's a little bit steeper. And at the end, it's below x to the 1/2. And then I'm going to do the green one is x to the 1/6. So let's make some statements about our graphs. Statement 1. All 1 over even number graphs go through 0, 0, and 1, 1. Now what does that mean? X to the 0th is 0. I don't have that right. 0 to the 1/2, or 1 over even, is 0. And 1 to the 1 over even is 1. What other things do you notice? If x is between 0 and 1, x to the 1/2 is less than x to the 1/4. If x is greater than 1, x to the 1/2 is greater than x to the 1/4. So in the first case, the smaller the power, the smaller the number. In the second case, the smaller the power, the bigger I'm sorry, not the small. The smaller, in the first case, the smaller the denominator, the smaller the fraction. In the second case, the smaller the fraction, the smaller the number. And then in the second case, the smaller the fraction. So those are the two words to pay attention to. Then it says, okay, so now you think you're so smart. Use the graph and given information so far, what do you think the graph of y equals x to the 1/8 will look like? So now I'm going to take this graph, and I'm out of colors. I'll use black. X to the 1/8. Well, it's going to go through this point and this point, and it's going to end up over here, right? So it's going to come in, go through 1, 1, but now it has to be above the green line. Okay? Part F says, if Q is a positive even number, the domain is from 0 to infinity. The range is from 0 up to infinity. And then the graph, 1 over Q as Q increases. Here's the best way that I think to say it. As Q increases, the corner gets sharper. So if you notice, you start here, x squared, you could take that corner at like 50 miles an hour. X to the 1/4, you better slow down when you get to the curve. X to the 1/6, you really better slow down as you get. X to the 1/8, you better be going like 30 miles an hour around that curve. As Q increases, the corner gets sharper. Okay? Next, number 3. Now we make them odd functions. You draw your functions, and I will take attendance. Nick, Michael,
Yep.
Marlena, Gavin, Janae, Felicia, Nicole, Eric,
Here.
Phil,
Back.
Grant, Connor, Eric, Laura, Madeline, Jessica, Lauren, Jake, Sam. Okay, so when you drew those, it looks like this: 1/3, 1/5, 1/7. So on my paper, I'm going to sketch those exact graphs there. This time, I've got 3 points I go through: 1, 1, 0, 0, -1, -1. And my purple is going to be x to the 1/3. So it comes in kind of goes around the corners and goes back out. Domain is from negative infinity to positive infinity. Range is also from negative infinity to positive infinity. Notice I used parentheses, right? Then, I forgot who was second. Purple or... No, it couldn't have been purple. X to the 1/5 is black. Ooh, I didn't write that one down. This is x to the 1/3. Now I'm going to do x to the 1/5. Comes in a little bit sharper after it goes through the corner. Goes down through 0, comes out a little bit sharper, and then goes out there. Okay, that's 1/5. And then red was 1/7. And now it says, what would 1/9 be? Using what you know, what's 1/9? Well, it's going to be below 1/7 there. Take the sharpest corner, come out the sharpest corner, and make sure it's above the x to the 1/7. Then it says, given the value of x, how do you compare x to the 1/3, x to the 1/5, x to the 1/7? Well, we have 3 different sections of our graph. For the interval from negative infinity to negative 1, the greatest q as q increases, or is it p? What letter are we using? Q. As q increases, so here's 3, 5, 7, 9. As q increases, x to the 1/q increases, right? Because the green one is the greatest, the purple one is the smallest. Then for the interval from -1 to to 0, as q increases, x to the 1/q decreases. Then if you go from 0 to +1, it's the same as this one back here. And if you go from +1 to infinity, it's this one here. Okay, now really what I should do is make sure these are all open intervals in here, because at -1 they're all equal, at 0 they're all equal, and at +1 they're all equal, right? X to the whatever power it is always going to be equal at those 3 spots. Page 2 23. Let x equal, or y equal x to the p over q. P over q is in its lowest terms. Explain why there are only 3 options, it says. If the 3 choices are P is odd, Q is even, P is odd, Q is odd, P is even, Q is odd. Why isn't there one more choice? What would the one more choice be? Menominee, say something.
Yeah.
Hello?
I want to switch the picture to away from Chippewa. Those guys out in the hall were talking, and so, you got to talk more.
Hello?
Stupid thing. Why does it do that?
I don't know.
Love this class.
I love this. 8 of the day for him. I don't know even who you were. I'll just have to give everybody in Menominee an A.
There we go.
Sounds good.
Keep talking. There you go. Okay.
There we go.
What a shame.
Why is there not one more choice? What would the one more choice be? Why can't they both be even? Like, say, 6 over 8.
Because it would make it a negative number because
6 over 8? No, it's still a fraction. You can divide both. Remember, it says P over Q is in simplest terms, okay? I think they say reduced to lowest terms. I can't remember. Is reduced to lowest terms. So these are our 3 options. B, if P is odd and Q is even. Okay, so we're going to do y equals x to the even over odd. Okay, so I'm going to graph y equals x to the even over odd. I got to turn these off first. Oh, I never turned on x to the 1/9. Oh well. Even over odd. Where are we? Here we go. Here's an even over an odd. 2 over 5. I'm going to make this one 8 over 7, just so that the bigger number is on top. Do you see how that changes our fraction? Our function. Okay.
2 over 1.
2 over 1, that would be a quadratic.
Oh, okay.
Okay, here we go. Describe the domain and the range, as well as the intervals over which the function is increasing and decreasing. So the domain is from 0 to infinity, right? Oh, negative infinity to positive infinity, right? The range is from 0 up to infinity, right? I'm going to put a sketch onto my paper also. This is if the even number is bigger than the odd number. This is if the even number is smaller. Oops, I didn't make my O big enough. The even number is smaller than the odd number. What can you say about the domain and range, as well as the interval over which the function is increasing? So everybody agree it's increasing here, and here it's decreasing, right? So it's increasing from 0 to infinity. It's decreasing from negative infinity to 0. That's the first one. Second one. If P is odd and Q is odd. Okay, so I have 9 over 5, 5 over 9. Y equals x to the odd over odd. I'm going to sketch my graph. And if the bigger number is on top, it's going to curve up. So x to the odd over odd, it's going to curve up. And if x to the odd over odd, if the littler number is on top, it's going to curve out. Okay, domain is from negative infinity to positive infinity. Range is from negative infinity to positive infinity. And it's always increasing, right? Everybody agree? Last one, part D. Y equals x to the even over odd. So I have a couple of those graphed here. Where'd it go? Even over odd. Here we go. No, we did even over odd. Odd over even. Oh, I must have switched A, B, and D around, huh? Odd over even. Didn't we do this one? Odd over even, odd over odd, odd over even. Let's try this. There we go. Notice we only have to be in the first quadrant, correct? If the numerator is bigger, it curves up. So x to the odd over a little even. And if the denominator is bigger, it curves out. In both cases, the function is always increasing. Oops, I didn't go to my notes there. Describe the domain and range. So the domain is 0 to infinity. The range is, actually it's bracket 0 to infinity, and it's always increasing. So if you go back and look at those heart rate functions, in every case, as it got heavier, the heart rate was always decreasing. Remember, it was to the negative, so it was always decreasing. And then when we did metabolic rate with mass, the heavier it got, the more food it always needed. It never needed less food as you were going along. We'll take our break. When we come back, it'll be 10:05.
Okay. So I think much please. I would just stayed up because I wouldn't be able to get up again. I actually ended up on this. I decided after this one.
There's no sociology.
Nope, she gave us homework though. Of course.
That's why I've never once been tempted to skip that class because
You get 5 times the homework than what you would have done in class.
well, I'm signed up for the like
You're rust up for
At least it's something.
the diversity one or whatever that she teaches, like race or whatever that transfers. That's all online.
Yeah, it's gonna be painful if I signed up for it next semester.
I was like, I know I need this, but maybe I just want to drag this out a little bit longer because I really don't want to have to do all of the extra work. Especially if I'm taking, I love history, but I'm feeling it's a lot of memorization. I'm really bad at that, which is too bad.
Yeah, she sent out an email, so we got a worksheet to do the June Wednesday.
Oh, no. But then I guess that means that the one plus for me is that was Did you have to enjoy the college?
Yeah, all of this in college.
Yeah. It's like the day before, my mother was like, oh my god, there's no space for anything. You need to eat all these leftovers. So I
as long as you can, and then be like,
got to Thanksgiving Day. I was like, you know what, I'm not even hungry right now, but I still ate 3 plates of food. Mistakes were made. My dad was like, yeah, let's go outside and put all the lights on. That sounds like something you take hard pass on. I love it. So. Also, I appreciate still being on health insurance.
That's the idea.
As much of a gambler as I am, I think I'm nice on that.
and these are almost this is ready.
Just going off of I always get more just because of that first laptop I ever had. To Dell and Sprung. I had to go in so many times to Best Buy if I didn't have to. It was costing me easily over $600 because they won't even look at it. Less than and yeah, happened with my first which is why it's still doing well. And there's some things that are wrong with it, but I refuse to take it in because I don't want to. As long as it works.
Okay. Page 225. New concept. Discontinuities of rational functions. Now, a continuity would be the function always has a value. There are two types of discontinuities, wholes and asymptotes. Here's a whole in a function. Do you see why they call it a whole?
Yes.
It's a value that doesn't exist. Okay? Here's how a function has an asymptote. Comes along like this and just disappears up into the clouds. And then after that, it starts at negative infinity and just continues on. Those are the two different kinds of discontinuities that we're going to be talking about. Discontinuities only appear in rational functions, like g of x is x squared minus 1 over x plus 1. Or like f of x is 1 over x. Graph the function g of x equals x squared minus 1 over x plus 1 using technology. Okay, x squared minus 1 over x plus 1. When I graph it, it looks like a line. But then it says, go to f or g of negative 1. So I'm going to go back here to negative 1. I'm going to go to my graph, and I'm going to click on it. And it says negative 1 undefined. So when I graph it, I'm going to graph the line. It goes like this. And then when I get to negative 1, it says it's undefined. Graph the function 1 over x. So I'm going to graph it on the same axes. 1 over x. And it looks like that. Then it says, oh, I'm sorry. We were looking for g of negative 1. Now we're supposed to find f of 0. So if x is 0, you see what happens? There is no value. It is undefined. So a discontinuity is a spot where the graph is undefined. There are two ways it can be undefined. One is as a whole. The other is as an asymptote. Boyle's law states that the pressure of a gas is inversely proportional to the volume of a gas. So we would have, let's do the graph, P as a function of V is 6 over V. Now, volume is never going to be less than 0, so all we're going to do is have a graph that looks like this. In other words, the pressure times the volume is always going to be 6. So we will go through the point over 2 up 3, and we will go through the point over 3 up 2. We will go through the point over 1 up 6, and through the point over 6 up 1. Got it? So it's going to be a graph like that. Now we know it's an inverse graph because, number one, they told us it's an inverse graph. But number two, our variable is in the denominator. Okay? This graph has a vertical asymptote here at x equals 0. It also has a horizontal asymptote at y equals 0. So this one actually has two kinds of asymptotes, but for right now, we're only worried about the vertical asymptotes. So here we go. If the volume is 1, volume, 6 over volume. If the volume is 1, the pressure is 6. If the volume is 0.1, the pressure is 6 divided by 0.1, 60. If the pressure is 0.01, the volume is, if the volume is 0.01, the pressure is 600. So as the pressure increases, the volume decreases. So if you took a balloon deep into the ocean, what would happen to its volume? It'd get smaller and smaller and smaller and smaller. Does the volume of a submarine get smaller and smaller and smaller? No, right? Because we're only talking about the volume of air. It's the ideal gas law. It's not the ideal solid law. Solids you can't get to shrink. Liquids you can't get to shrink. Well, what happens, though, in a submarine as you get deeper and deeper? The pressure on the outside gets bigger, right? If you do not have a strong enough submarine, it's going to crunch like a tin can. I don't know if have they ever had a submarine that like crackled and sank? I know they've had ones that had like holes in them and they sank. That'd be a good internet extra credit problem, wouldn't it? Okay, so what happens to the pressure as the volume decreases? Volume decreases, pressure increases. Could the pressure ever exceed 1,000 atmospheres? Sure. 20,000 atmospheres? Sure. Okay? When it does, the volume is going to get smaller and smaller and smaller. And in fact, most gases if you put too much pressure on them, are no longer gases. They'll become a liquid or a solid. Hey, did you hear about the guy over in Minneapolis that died of carbon dioxide poisoning? He was delivering to McDonald's. Anybody know what he is delivering? Dry ice. And his truck malfunctioned. He tried to fix it. Dumb idea. Okay? If your carbon dioxide is leaking, don't try to fix it. He was overcome with carbon dioxide and he died. Yeah, they just identified the guy. Okay. In an earlier scenario, you worked with the height of a ball was given by h equals negative 4.9 t squared plus 20t, where t was measured in seconds. And the average change of height gives the information about the velocity of the ball. Find an expression for the average velocity of the ball from t equals 1 to t equals 1 plus delta 1. So, A as a function of velocity is, remember this is not the function, the height function, this is the, actually it should be A as a function of t. A as a function of t is, so it's the h of t plus 1, or t plus delta t, sorry, minus h of t over t plus delta t minus t. Remember, it's the change in the function divided by the change in the time. Okay, so let's go through. You have to write really small here. In fact, I got to get out my glasses so that I can do this. So, A of t is, for our numerator, we have negative 4.9 times t plus delta t squared plus 20 times t plus delta t. Subtract negative 4.9 times t squared plus 20 times t over t plus delta t minus t is just delta t. It says you do not need to simplify your expression. What is the domain? Delta t does not equal, it's the only thing delta t can't be. Zero, right? Does this make sense in the context of our rate of change? Sure, let's talk about it this way. What's this slope here? Well, you could figure it out, right? What's the slope here? You can figure it out, right? You can figure it out, right? How can you figure out the slope if those 2 points are the exact same point? You can't. There is no change in x. There is no change in y. They're the same number. So does it make sense in this context? Yes. So let's go through it and fill out these numbers here. Okay? So, let's see here. We did that one. Okay, here we go. So on this function, I put negative 4.9 times 1 plus delta x, or x1, plus 20 times delta x plus 4.9 minus 20. Now, why did I write plus 4.9 minus 20? What did it say t was? It said where t equals 1. So this becomes negative 4.9, and this becomes just plain old 20. So those two numbers just stay where they are. So let's look here at our function and see what we can see. So I have these points, and I graph them. If x is 1, f of x is 5.3. If x is 0.1, f of x is 9.78. 0.01, 10.15. 0.001, 10.1995, and 0.00001, 10.1995. Do I have too many zeros? Yeah, I did one extra point, didn't I? So, we keep getting those points closer and closer together. What happens to the velocity? It gets closer and closer and closer to 10.2. So the slope here at 1, so if we go up here to the number 1, one is where we cross the x-axis here, right? So where we cross this axis, if we take our ruler and see, well, what is the slope at that point? What number would you expect it to be? 10.2, right? So the slope at that point is 10.2. And in fact, as I zoom in here, let's graph from 0.9 up to 1, and let's graph from 15 up to 17.1.1. So if you notice, as we graph that, what does that curve look like at this point? Looks almost like a line, right? We zoomed in so far, it looks like a line. When graphing, the average rate of change function, A of t, as delta t gets closer to 0, the or A of t gets closer to the rate of change. In other words, it becomes a linear function. So if we look back at our graph here, and we go from 0 Well, let's go from negative 10 to positive 10. And let's do y from negative 100 to positive 100, just so that we can see the whole thing. And we've got our height function. Right here is red. I should turn everything else off so that you can see it. And we've got our height function. What do you see? So our function starts at 0, it goes up. We threw a ball up into the air, it comes back down. It says, what is the domain of the average rate of change? So this green function, what's happening from 0 as you go forward? It goes from 0, or I'm sorry, it goes from whatever that value is, 29 or something like that. And it keeps on decreasing to negative infinity, right? So its domain is from 20 to negative infinity, right? From 20 to negative infinity, and it's always decreasing. Does that make sense? You throw a ball up into the air, what's going to be true about its velocity? It's going to keep on slowing down, slowing down, slowing down until it can't slow down anymore. It's now going 0. Then what's it going to do? Keep on slowing down, and now it's going backwards, right? It's going back down. For any values, what happens to the delta t as t approaches 0? As it approaches 0, it got closer and closer to 10.2, right? What behavior did you, what values of delta t are not in the domain? Decide if they represent removable and non-removable discontinuities. So over on this page, what is true about this function right here? What could we do with that function? So I factored the numerator, and I got x plus 1 times x minus 1. What's the denominator? X plus 1. What can I do with that function? Right? I can cross off. So a whole has a factor that can be crossed off. Can be simplified maybe. An asymptote, all denominator factors can't be eliminated. Page 229. Let's first talk about the discontinuities of 16b. The first one says m as a function of x is 3x squared plus, what does your book have there? Does it say 12 or does it say 12x?
All that.
Over 4 plus x squared. Can we remove 4 plus x squared? Can we factor the numerator so that we have 4 plus x squared as one of the factors? Well, if we took a 3 out of this, what would we have left? X squared plus 4x, correct? Is it removable? Not removable, right? So it's going to be a vertical asymptote. Let's look at the next one. N of x equals 3x squared over x squared. Now, is it removable? Can you factor this fraction? Yeah, you can cancel out the x squareds, right? So it is removable. So it's a whole. Vertical asymptote in the first case, a whole in the second case. But that's not what we're talking about in this lesson. In this lesson, we're talking about the end behavior. Or in other words, as x gets closer to negative infinity, or as x gets closer to positive infinity. So we're not talking about the middle part of the graph, we're talking about the end parts of the graph. How are the two functions related? Well, they both are rational functions. Graph the two in the same window. So I graphed them both. And if you notice, I don't know what that there is. If you notice, the second one, we don't have a hole there. In the first one, as we get closer and closer to 0, it was there, it became undefined. So let's graph those two on our paper. So the red one, notice in both cases, we were around 3. Then let's look at the second one. And if you note, I'll go back and draw it again. For the second one, we were above 3, and then we went down through our graph, through 0, 0, went down a little bit further, came back up, and we went to negative infinity. So our graph looked something like this. Okay, so here's our graph. We aren't talking about what happens in this part. We're talking about as we go farther and farther this way. So as I go farther and farther this way, what happens to the value of our function? say I would just keep on walking that direction forever and ever and ever, where would I end up? Look at your graph. What value? How high up was this line? Look at your graph. Did you guys graph it? Anybody graph it? Desmos? Do it quick. Do the first one, 3x squared plus 12x over 4 plus x squared. Where'd you end up? Menominee, you got to talk again. Chip was louder than you.
Hey, what's up? There we go.
There you go. Okay. What'd you get? What value is that? My second letter is all, or my second number is always 3, right? So as I go farther and farther left, farther and farther right, my y value, it gets closer and closer to 3. For the red line, it gets closer and closer from the bottom, if it's negative, from the top, if it's positive. But in both cases, they both approach 3 at negative infinity and at infinity, right? They both approach it regardless of whether they were positive or negative. But why? Three x squared over x squared. I'm only going to list the important parts for both of these. That's the second one. The first one is also 3 x squared over x squared. Now notice the x squared in the denominator isn't the first term, it's the second term. But in both cases, here's the important part. Those are the same. Those are the same. So if the highest powers, the same, look at the coefficient. The coefficient here is 3, so the end behavior is 3. Page 229. This activity will model the effective population size presented in preview assignment 16B. Here's what the effective population size is. In order to make sure there's enough biodiversity, you take 4 times the number of males times the number of females divided by the sum of the number of males and the number of females. So they give us an example for, suppose a population has a single male. What does this formula become? Well, if it has a single male, we would take 4 times 1 times the number of females divided by the number of females plus 1. So 1 male, our formula becomes the effective population is 4 number of females divided by number of females plus 1. What's the leading coefficient in the numerator? Leading coefficient in the denominator. Be careful, it's not 0. If there's not one there, there's 1. Yes. So, fellas, when you get married and you go to the bar, don't forget you still have one wife. All right? Don't forget that. Even though you don't have a count on them, okay, there is still one there. Assume there is one there. All right. If it was 0, we would have put 0, but there's not. So we have 4 divided by 1, which is 4. Graph the function you found in part A. Let's predict what we get for our effective population size. So here we go. What happens as we get farther and farther along here? Our population keeps getting closer and closer to 4, right? As we go negative, it keeps getting closer and closer to 4, but it's coming from the top, right? So our end behavior is 4. Number 3. Suppose a population has 3 more males than females. So now we have the effective population is 4 times the number of males. Number of females plus the number of females plus 3, right? It has 3 more males. No, it's not plus, it's times. The number of females plus 3 divided by the number of females plus the number of females plus 3, which is, this part here is 2 number of females plus 3. So in the numerator, we have 4 number of females squared plus 12 number of females. In the denominator, we have 2 number of females plus 3. The first thing you will notice when you graph it no, that's not the one that we had. 2x, 12x squared. Yeah, that is. 2x plus 3. The first thing you will notice is that there is a vertical asymptote, right? Because as you go farther and farther along, you get to a point where you can't go any further. Then you start all over again at the bottom, and you go up. What is that number? It's where 2x plus 3 equals 0, or in other words, x equals negative 3 halves. But the other thing that you notice is, as you go closer and closer to infinity, what keeps happening to the value of your graph? It keeps getting bigger and bigger and bigger. So in this case, we would say the end behavior is infinity. Why? Notice the numerator and the denominator do not have the same power. Before, the numerator and denominator did have the same power. Okay, there are 4 choices that we're going to graph on page 230. Important stuff. Okay, now for the other algebra class, they were like, oh, Kevin, I never pay attention to when you say important stuff. So, I said, okay, don't. Here we go. There are four cases for what happens. The numerator power is little, and the denominator power is big. The numerator power is the same as the denominator power. The numerator power is 1 bigger than the denominator power, and the numerator power is bigger than the denominator power. So I'll give you some examples for each one of those so that you can write them down. So let's say that for this first one, t to the third, what would the denominator have to be? T to the, or give me an example of what it could be. 15. If that is true, there is a horizontal asymptote, and that horizontal asymptote, the bigger number I get, the closer it gets to 0. Why is that so? Well, think about it. Eventually, you would run out of t's if you were going to cancel, correct? You would have 1 over t to the 12th. So I have 1 pizza, and t to the 12th people I'm going to give it to. And let's say t is 1 billion. So I have 1 billion to the 12th people to give that 1 pizza to. How much is each person going to get? Butkus, right? I mean, you're not going to get any pizza. Sorry, Charlie. So as this number gets bigger, it gets closer and closer to 0. Okay, next case. Give me a t. I'm sorry, a power. Let's say 4th. What will the denominator power have to be? T to the 4th, right? If the powers are the same, I pay attention to the coefficients. 15 on the top, 20 on the bottom. What's 15 divided by 20? 0.75, right? So as I get closer and closer to infinity, my answer gets closer and closer to 0. So let's say I had 1 billion people. 1 billion to the 4th divided by 1 billion to the 4th. Everybody agree those two are going to cancel out? What am I left with? I'm left with 15 over 20. 15 over 20 is 0.75. Okay? The next one. In our example that we just had, the numerator power was 2. So let's say our numerator power is 2. What is going to have to be the denominator power? There's only one number that it can be. T to the 1st, right? It can only be t to the 1st. So now I look at the coefficients, 45 divided by 3, and it's a slant asymptote that has a slope of 15. So if you look back at the graph that we just did, I'm going to zoom out here on our graph. Oh, come on. Negative 200 to positive 200. Let's go from negative 1,000 to positive 1,000. And if you notice, it looks like a line, right? But then if you look right here in the middle, it's got a straight up and down and a straight up and down. So this line has a slope, in this case, of 4 over 2, which is 2, or in our case that we just drew, 15 over, or 45 over 3, which is 15. Last case, the numerator power is bigger than the denominator power, so let's say t to the, give me a power, 10. So the denominator can be any number that is less than 10. 7. There is no asymptote. And you think, well, why is that so? Well, if you keep on canceling here, eventually you will get t to the third on top, right? So if you take 1,000,000 to the third, that's a really big number. 1,000,001 to the third, that's even bigger. So it just keeps on, as you go farther and farther over, it keeps getting bigger and bigger and bigger, and there is no end behavior. Okay, so we would say for this one, end behavior is 0. End behavior is 0.75. End behavior is still infinity, but there's a slant asymptote. And here, end behavior is just plain keeps getting bigger and bigger and bigger. (17A) next time.
She said so. Well, yeah, but we never, there's like no study guides. So we don't know what's on it.
I don't know.